Well, finally made it to the last section. Obviously section 11.7. And really, this is just mainly conversions, this entire section. So we're going to look at cylindrical and spherical coordinates to represent surfaces in space. And sometimes it's easier to graph polar coordinates than rectangular, and then it's a similar situation with space coordinate systems. So that's what we're going to look at, and it's really a lot of conversions going between rectangular, cylindrical, and spherical. So the cylindrical coordinate system, it's an extension of your polar coordinates in the plane to three-dimensional space. So usually, obviously, if for polar coordinates, we usually have r theta. Well, we want to put this into space. So our point P is represented by an ordered triple, and our ordered triple is going to be r theta. So that stuff stays the same, but then we need to have our third variable in there, and our third variable is just z. So looking at this, r theta is our polar representation of the projection of P in our xy plane, and then this z is the directed distance from r theta to P, to our point. What we really have to look at here is how we can do conversions, and they really don't change very much. So if we're converting cylindrical to rectangular, I have cylindrical, that means, and I want to create rectangular. Rectangular means that I have to have what is x equal to, what is y equal to, and what is z equal to. Well, the nice thing is this really doesn't change because I already know for polar how to create it. So I know that x is equal to r cosine theta, and we did that back in chapter 10. And we know that y is equal to r sine theta. And in this situation, it's really nice because this z is just equivalent to your z value. So this conversion is a pretty easy conversion for us to do. If we have to convert rectangular to cylindrical, so I have rectangular, I have x, y, and z, and I want to create my cylindrical, meaning I have to create figure out what is r, what is theta, and what is z. Well, this stuff we should know, we should remember it. So if I have to create r, and remember it's rectangular to start, so I have x, y, and z. This was just the square root of x squared plus y squared, exactly what we did in chapter 10. Theta is still that arctangent y divided by x. And remember, arctangency inverse, this is a ratio, so it's going to create theta, an angle. And then here's z is still just equal to z. So converting cylindrical is just, it's three-dimensional for polar, but otherwise the rules that we've learned have stayed. 0, 0, 0 is still called the pole. Just like in our two-dimensional sense, 0, 0 was the pole. And the representation of a point in the polar coordinate system is not unique. Remember, if it's not unique, it means that there can be more than one answer and more than one correct answer for this. And it follows that the representation of your cylindrical coordinate system is also not going to be unique. So there's lots of different ways that we can represent the same point. So looking at some examples, we want to convert 1, 3 pi over 2, and 1 from cylindrical coordinates to rectangular coordinates. Well, usually what I do to help myself out is I say this is r, this is theta, and this is z. And then I know I have to create rectangular coordinates. So I just say, okay, well then my rectangular, I want what is x, what is y, what is z. Well, remember, if we follow the rules up above, we know that x is equivalent to r cosine theta. So really I can just put in there that it's 1 times cosine theta, which is 3 pi over 2. When we evaluate this, cosine of 3 pi over 2 is equivalent to 0. So here x is just 0. Y is r sine theta. So it's 1 times sine, our theta value, 3 pi over 2. Sine of 3 pi over 2 is a negative 1. So negative 1 times 1, we get negative 1 for an answer. And then z, remember, was just equal to z. So z is 1 z is still just equal to 1. So now our point in rectangular would be 0, -1, 1. And going the opposite way, we want to convert the point -3 to -1 from rectangular to cylindrical. And I take the same approach where I say, alright, this is rectangular, so it's x, y, and z. And I want to create cylindrical. So cylindrical, I need to know what is r, what is theta, and what is z. And you should pause this and try to do this on your own. Alright, so then if we look at this, we know r is equal to the square root of x squared plus y squared, so that gives us square root of 13. In this situation, I always want to keep everything in radians, but this just isn't nice. We're arctangent of 2 divided by -3, and so we're actually we'd leave it like this. You don't even have to write it as a decimal. And then z is obviously -1. So our point, I'd rather have it exact. So square root of 13, this arctangent, -2/3, and -1. So that would be our point, the cylindrical coordinates for that point. Another type of example that we have is to find an equation in cylindrical coordinates for the surface represented by each rectangular equation. So obviously this is these are rectangular because I'm in terms of x, y, and z. Here I just have y and x, and that's okay. I don't need to have a z. But I have to convert everything, and I want to take this equation and write it in the cylindrical coordinates. Therefore, if I have to use cylindrical coordinates, my equation can only have r, theta, and z in it. And there's a lot of different ways that you can approach this. Sometimes you see shortcuts, or maybe you don't see the shortcuts, but you see something that happens that makes it simple really, really quickly. And other times you may struggle and write a whole heck of a lot. Looking at this one, as soon as I see x squared plus y squared, we know that that's equal to r squared. So keep that one in mind. Otherwise, you could replace x. We know that x is r times cosine theta. So if it's x squared, it would be r squared times cosine squared theta. But this is much quicker just to realize x squared plus y squared is equal to r squared. And then I don't have to convert z's because z is part of the equation, or part of our variables for cylindrical coordinates. So that made that problem go really, really fast because I noticed the x squared plus y squared. And like I was saying before, otherwise x squared is r squared times cosine squared theta. Y squared is r squared times sine squared theta. Well, then you can factor an r squared out of this, and you're left with cosine squared plus sine squared, which is 1, and so you're left with r squared anyway. So that's obviously the nice, quick way of doing it. It also works this way if we need to. Yeah, maybe not cross it off if we don't want. No, it works there. In this situation, we have just y squared and just an x. So obviously we can't do the same approach we did for number 20. And for y squared, that means it's r squared times sine squared of theta. X is equal to r cosine theta. And really what we want to try to do here, usually we want to try and solve for r. One kind of unique thing that we can do is that we can divide by our variables. So if I want to solve for r, I'm going to divide by r at least, in that way, so that here now on the left side I only have r. And now I want to have the thetas together, so if I divide by sine squared to both sides, I have cosine over sine squared, and you could leave it like that. It probably isn't the end of the world. But cosine over sine we know is cotangent. And then if you have sine in the denominator, we know that that's the same thing as cosecant. And the book may do a lot of simplifying and crazy things, but that definitely works out to write it in we wrote it in a cylindrical coordinates. And the last one now, find an equation in rectangular coordinates. So rectangular obviously means that we just want x, y, and z, the and we've been given cylindrical equations. The first one here, when we have just theta given to us, we know that we like to use the trig function tangent with things, and that can help us get theta, evaluate, and figure out what theta is here. I guess how I started this one is I just said that tangent of theta is equal to y divided by x. And why we use tangent, obviously, it's because it uses y and x, the two variables that we want for rectangular. So if you use sine, we know that sine is y over r. Well, we don't want r, so you'd have to rewrite r. So it's a lot easier to always use tangent. Well, now I can evaluate this, and if I know theta is 2 pi over 3, I'm going to plug that in there. So I have tangent 2 pi over 3 is equal to y divided by x. And when I solve for this portion of it, tangent of 2 pi over 3, that's a 120 degree angle. So basically that's a negative square root of 3 equals y divided by x. And now a couple different ways that we could write this. Multiply the x over, so then we can say, well, y equals negative x square root of 3 is one way to write it. Or sometimes they solve and they say 0 is equal to. So if we let everything equal 0, I'm going to add the square root of 3, or negative x plus square root of 3 over here. So then I'd have x square root of 3 plus y equals 0. They like to write the equations equal to 0. Either one of them would work there. And this last one, if we have r squared times cosine of 2 theta. 2 theta isn't good because that gives us a double angle, so we have to get rid of that double angle. And then we're adding z squared plus 1, obviously, and set that equal to 0. So if you don't remember your double angles, and the trig function's in the front cover of your book, but you have to replace that double angle right away. And cosine of 2 theta is one form is cosine squared minus sine squared. And I like that because then I know I can distribute and have the r squared cosine squared, r squared sine squared, and I know that that's really nice to have. And then I'm still going to just add on the z squared plus 1 equals 0. So if I distributed this to both, obviously I'd have r squared cosine squared theta minus r squared sine squared theta plus z squared plus 1 equals 0. And this is very convenient that we have both r squared and cosine squared, and obviously same in this term, because we know that r cosine of theta is equal to y. Well, if they're both it's equal to x, and if they're both squared, well then we just would have x squared minus, you have an r squared and the sine squared, so that gives us y squared, and then plus our z squared, which we can have z. Obviously for rectangular we need x, y, and z, plus 1 equals 0. So those are pretty easy conversions, nothing too different from what we've done in the past. And z is equal to z, so that actually makes it really, really nice. Moving on to the spherical coordinates. For spherical coordinates, this system is similar to the latitude-longitude system used to identify points on the surface of Earth. And so each point is going to be represented by an ordered triple, which obviously makes sense if we're in 3 dimensions. And our ordered triple for this is going to be the Greek letter rho, which is an italicized p, theta, and then our third coordinate is going to be phi. So our 3 Greek letters here. Well, to write these out, we know that rho, that's R-O-H. Rho is equal to the distance between the point on the surface and the origin. Distance between the point on the surface and the origin. Our second coordinate is theta, and theta is equal to the angle from the positive x-axis counterclockwise to the point. So the angle from the positive x-axis positive x-axis counterclockwise to the point. And then our third coordinate, phi, just kidding, phi, whoa, it's phi, that's an I, not an E. So phi is equal to the angle from the positive z-axis to our segment OP. And P, O is the origin, and P is our point. The angle from the positive z-axis to the segment OP. So if we look at this specific point that we have here, and we're going to consider, like, obviously this is going to be Earth, and we consider Earth just in general to have a radius of 4,000 miles. In order to write this coordinate as a spherical coordinate, remember that rho is the distance between the point on the surface and the origin. So any surface on Earth, that will give us 4,000. Theta is the angle from the positive x-axis. So here it would be our positive x-axis counterclockwise to our point. And if we're going counterclockwise we should usually go this way to get to y. Well, in this situation, we're going obviously clockwise, so that would make it just a negative 80 degrees. And then phi, our last one, is our angle from our segment, from the positive z-axis to our segment. And so in this situation, positive z-axis, if we go to our segment, that would just give us 40 degrees. So that's where our spherical coordinates are going to be used. To convert our spherical to rectangular, obviously spherical, we know that we have it because we'll have rho, theta, and phi. And then we want rectangular, so we want to create rectangular, meaning we want x, we want y, we want z. These are definitely harder than when we went to our cylindrical. The equation for this is rho times sine phi times cosine theta, which is really ugly, and really it does just come down to kind of memorization of it. Our y is very similar though. It's rho times sine phi times sine theta. So what I do for both of these, I know that the first part of it is, for both of them, it's rho sine phi, and obviously rho sine phi, and then I know that x corresponds with cosine. So x is and then I get my cosine from there. And z is equal to rho times cosine phi. If we have to convert from rectangular, so we have x, y, and z, and we want spherical, we need rho, we need theta, we need phi. So rho is equivalent to the square root of x squared plus y squared plus z squared. Theta is still arctangent y divided by x, so that's pretty nice. And then phi, just to make things difficult, which is kind of ugly, it's arc cosine z divided by the square root of, well, it's basically z divided by phi, or by rho, I'm sorry. So z divided by rho, well, rho over here is the square root of x squared plus y squared plus z squared. And truthfully, this is the only conversions. I keep these two memorized because I always figure I can always go from rectangular, and then I can go from rectangular to cylindrical pretty easily. So these next ones, I don't deal with them. I always say if I can make it rectangular good enough, I can go from there and I can figure out anything from there. But if we did want to go from, because maybe you're good at remembering things or whatever, from spherical to cylindrical, remember, we just said we need what is r, what is theta, what is z. Well, r is equivalent to the square root of rho squared times sine squared phi. Theta is just theta, so that's pretty nice. And z, because it's the same z, it's rho times cosine phi. And if you convert cylindrical to spherical, okay, so if you want spherical, you need rho, you need theta, you need phi. Rho is the square root of r squared plus z squared. The theta is nice. Theta is just theta, so that's nice. And phi is arc cosine z divided by the square root of r squared plus z squared. So a lot of conversions here, a lot of different conversions that we can have. I always say if I can get it to rectangular, I can do anything from there. So these are the two that I keep in mind and I use. I don't particularly love just memorizing equations. I think that's kind of crazy, but it is what it is. And so our purpose here is to be able to convert from one set of coordinates to another. And so the spherical coordinate system down at the bottom is used primarily for surfaces in space that have a point or a center of symmetry. Alright, so looking at some examples, some obviously converting here. We want to convert our rectangular points. So rectangular, I know I have x, I know I have y, I know I have z. And we want to make them spherical coordinates. So spherical means I need rho, I need theta, I need phi. Rho, square root of x squared plus y squared plus z squared. And then that's obviously very easy to calculate. I'll start with the harder one here. That would give us 16 times 2, so 32, plus that squared will give us 4, so that was up to 36. That squared is 4 more, so we're 40. And the square root of 40 then would be 2 square root of 10. Theta is just like we've been doing, so it's still arctangent of y divided by x. So 2 over 2, which is 1. Arctangent 1 is going to give us pi over 4. It's kind of a nice one. It worked out really well. And then phi is your arc cosine. It's z, remember, divided by the square root of x squared plus y squared plus z squared. Therefore, we have arc cosine. Our z value is 4 square root of 2 divided by, we already calculated this. We know that this is rho, square root of x squared plus y squared plus z squared, and that gives us 2 square root of 10. Just simplify down the best you can, so that will simplify out and give us 2. If you plug it into your calculator, I can't imagine it's going to be anything pretty. It's got to be some ugly mess. If we multiply them by square root of 10 over square root of 10, this will end up giving us now square root of 20, which is 2 square root of 5. Oh boy, better start rewriting. So if this is equivalent to 2 square root of 5 times 2, that gives me 4 square root of 5. And then in the denominator, I still have that would give me 10. Oh boy. 4/10 then we know can simplify down to 2/5. So a lot of simplifying radicals there. Obviously, if you have the formulas, it's incredibly easy to do. And we want to convert our spherical coordinates now to rectangle. So spherical, I always think, okay, and I think it's really, really helpful to label them above. I have rho, I have theta, I have phi. I want rectangular, therefore I want x, I want y, I want z. This is a kind of ugly one. So x is equal to rho. Maybe we should write it out. Rho times sine phi times cosine theta, where y is rho times sine phi times cosine theta. Just kidding. That's totally y. Y always goes with sine. That better be a sine theta. Plus, we know the equations aren't going to be the same. And z is equal to rho times cosine phi. Well, now it's, again, once you have the equation, it's super easy to plug in. So we have 9 times sine pi. Sine of pi is just equal to 0. So that's really nice. And we don't really care now what cosine of theta is, square root of 2 over 2, but really it's meaningless. So x is equivalent to 0. Well, we also know in this situation, y, we have rho, we're going to end up with, if we have sine of pi, I thought that was going to simplify out again. They would if they were different situation, obviously. Sine of pi is going to give us, I gotta think real quick. That should still be 0. I had a brain lapse there. I thought I was evaluating pi over 4 for a second. I'm not really sure what was going on with me. But obviously, if this sine phi is equal to 0, that sine phi is still going to equal 0. And then I don't really care the sine of pi over 4. That's meaningless. I know that y, no matter what, is going to equal 0 there. And now for z, rho is 9 times cosine cosine phi, which is cosine pi. Cosine of pi is -1, so z is going to equal -9. Therefore, my point is 0, 0, -9. Oh, all right. Last page. 44 and 46. We want to find our equation in spherical coordinates for the surface represented by each rectangular equation. So obviously looking at it, it's rectangular. We have x, y, and z. We want spherical. We want rho, theta, phi. And I sometimes just do it the really long way. So in this situation, if you can remember what x is, well, I have x squared. To say x squared plus y squared is r squared, you can do that and then do your conversion. Well, what is r squared equal to? And that also works well too. It actually is a little bit quicker, but I think most of you in general, if you see x, you're going to say, well, I know what x is equal to. If I square it, I can figure out what that is too. So we know that x is rho times sine phi times cosine theta. Well, I just have to square everything. So it's rho squared times sine squared phi times cosine squared theta. And that takes the place of x, or x squared. Y squared is rho squared times sine squared phi. And now because it's y, now it's sine squared theta. Minus 3, our z value, again, we can just remember that z is equivalent to rho times cosine phi. So then you just square it. So it's rho squared times cosine squared phi. And that equals 0. So really, really ugly. Yeah, absolutely it is. Here we can say I have the cosine squared and sine squared, and obviously we could factor out rho squared times sine squared phi. Then we're left with cosine squared theta plus sine squared theta. And then we have minus our 3 rho squared cosine squared phi equals 0. Well, this is obviously 1, which does clean up a little bit. Gets rid of some stuff, I guess. And then minus 3 rho squared cosine squared phi equals 0. And here, I don't care if you don't factor out the phi squared. If you don't use your double angles, I'm completely fine with that. 'Cause I know, like, you don't have to try to create crazy things. As long as you convert everything, then good to go. So here, this is now a really simple one. What is x equal to? Well, x is rho times sine phi times cosine theta. That equals 10. Good enough. We don't have x, y, and z, and instead we're in spherical coordinates with rho theta and phi. Okay, 54 and 52, we want to find an equation in rectangular coordinates, so we want to have x, y, and z in our answer for the surface represented by each spherical equation. So obviously spherical equation, We have rho and phi. We want to get rid of it. One thing ugly about this is that we never really deal with secant, cosecant, and cotangent. So that's kind of a hint, is I would get rid of this thing. And what you can do to get rid of it is say, well, I don't want secant. I'm going to say that this is rho is equal to 2 divided by cosine phi. And usually that's kind of a hint on what to do now. And then we have rho cosine phi equals 2. Well, we know that rho times cosine phi is equal to z, so z is equal to 2. So if you see one of our either secant or cosecant or cotangent, usually try to rewrite that, and that's kind of a hint on where to go. Otherwise, you're looking for those kind of ugly equations, like this one with the rho times cosine phi, or your rho times sine phi cosine theta, and they are kind of ugly to look for, and we just haven't done them before, so it's a little bit more difficult to recognize. The next one, we have that phi is equal to pi over 2. So to go from here, I guess I just took a trig function, but I wanted to eliminate this side as well. So sine, cosine, or tangent of pi over 2 would equal 0, because 0 is just handy. And I used cosine, because I know cosine of pi over 2 is 0. Well, if I take cosine to one side, we're the fairest people in math, we're going to take cosine to the other side as well. So we have cosine phi is equal to cosine pi over 2. Well, we know that cosine of pi over 2 is equivalent to 0. And now we have just cosine phi in here. And cosine phi is equivalent to, let's see, what can we do with cosine phi? We know that we want to keep as little as possible. We know that z is equal to rho times cosine phi. So in this situation, I can say that cosine phi is rho divided by z. Whoa, just kidding. Z divided by rho. So in this situation, z divided by rho will equal 0. And I want rectangular. So I can only have x, y, and z. I have to get rid of this rho. Well, now, what is rho in terms of rectangular? And we know that that rho is the square root of x squared plus y squared plus z squared. Well, technically, I didn't even really have to do this step, because if any fraction is going to equal 0, we know that it comes from the numerator. So really, in this situation, all we care about is that z is equivalent to 0. You shouldn't say all we care about, but that's what it kind of comes down to. 60 and 68, we want to convert from cylindrical to spherical. And so cylindrical, we know that we have r, theta, and z, and we want to convert to spherical. So spherical means that we need rho, we need theta, and we need phi. Excuse me. All right, well, what you can do is you could take these cylindrical points and convert them to rectangular, and then from rectangular to spherical. But also you can look at the formulas, and if you know the formulas, it's obviously quicker. It's one less step. So I'm going to use our formulas for this. I know that rho is equivalent to the square root of r squared plus z squared. I know that theta is equal to theta, so that's awesome. And then I know that phi is equivalent to arc cosine z divided by the square root of r squared plus z squared. Therefore, rho is going to equal the square root, let's calculate it. R squared will give me 4 plus 4, so the square root of 8 will give me 2 square root of 2. Theta is equal to theta. Awesome, I can do that one every time. And phi is equal to arc cosine, and we'd have our z value, negative 2, divided by this 2 square root of 2. So if we simplify that out, we have negative 1 over square root of 2, and we actually know this one. With the arc cosine, that obviously simplifies to negative square root of 2 over 2. And remember, way back, that cosine or principal values are quadrants 1 and 2. So if you want a 45-degree angle and it's negative, your angle it should be 3 pi over 4. Therefore, your coordinates now, 2 square root of 2, 2 pi over 3, and 3 pi over 4. And then the last one, convert from spherical to cylindrical. And I'll let you do this. Remember, spherical, here's rho, theta, phi. You want cylindrical, so you want r, you want theta, you want z. All right, so you figure out this one. You can obviously use your conversions to help you, and then check it. All right, so here you can check your answers. You should always simplify down radicals. Obviously solve our trig functions if we can, which you should be able to. And then you can write your cylindrical coordinates. And that's it. That's it for Calc 2. Kind of a nice thing. It's kind of a good feeling to be done with all the notes for it as well. Your homework is kind of a random, weird assignment. So there's so many different things, and so much of this, all it is conversions, which, again, like I said before, I don't particularly love, but it is what it is. So on page 825, the good problems are 1 through 71, the odds, 97 through 103, the odds, and I want you to choose problems that will help you be successful. If you know the formulas, it's going to work. You're going to be able to do these things, and you have 15 problems minimum to do. I would say, what I would suggest is to stay away from converting or do 1 or 2 from rectangular to cylindrical. You're really good at that. You already know that. So do the tougher ones, dealing with the spherical coordinates, just because that's really all completely brand new. And repetition and going over these formulas will help you remember them, because it's incredibly difficult to get the problem right if you don't know the formula. So a little repetition with it and practice it, and it really shouldn't be too bad. So I guess we'll say we're signing off with Calc 2. It's a really good feeling.